Look, thank you very much, Richard. It's lovely to be here. So this picture here is the RSV Noyena. It's going on its first marine science voyage. It arrived in 2021 and it's undertaking marine science research in Antarctica off what's called the Denman Glacier, and it's being complemented by a terrestrial component, the Denman Terrestrial Campaign. And the two together are somebody's dream experiment because it's been a decade in the plan, and the Southern Ocean and Antarctic community have come together to have that voyage. It's like the first serious marine science voyage in a decade. So follow the Twitter and the AAPP LinkedIn pages, because we'll give you regular updates on that. So it's a fantastic achievement at this moment for the Hobart. They left on Saturday. So what I'll do is, for the next 40 minutes, talk about the role of the Southern Ocean and Antarctica. Antarctica is very much part of this story. And let's see if I can work this. That's good. So I go to next, and maybe that worked. And so I'm really going to kind of give you an idea of why Antarctica is important, because I believe it's important. I'll give examples, not from my next job in the Laureate. I'll give examples actually from the Australian Antarctic Program Partnership. And I'll conclude a little bit about the urgency of what we need to do. So this picture here is sort of a snapshot, if you like, of the sorts of reasons that we think Antarctica is important. We often forget that Antarctica is actually owned by no single nation. It's run by a treaty system of 58 different countries, 29 who make the decisions and the other 29 participate. And there's three important things, and I love these three things, because the first is Antarctica will be used as a reserve for peaceful purposes. It will be used, continuing the extraordinary experiment in the late 1950s, the International Geophysical Year, for scientific purpose and scientific investigation, and continue to do that. And the third thing is that the treaty encompasses the idea that we'll protect the environment of Antarctica in an ongoing way. If you think about it, that's a pretty unusual set of rules for the operation and management of our biggest ice sheet on the planet Earth. But there are some challenges, if you like. There's pressure on the Antarctic treaty system. We know from the last IPCC reports, ecosystems are in decline, iconic species, some of them are near extinction, blue whales are an example. The resources are changing. And we also know that the achievements of the treaty system are eroding. There's much more tourism going to Antarctica, there's bird flu in Antarctica, and we know also that, and that's the subject of this talk, is that Antarctica is actually responding to climate change. It's lost mass, sea levels going up, and there are consequences with that. Sea level erosion around Antarctica. You often think that Antarctica is a long way away, but actually it's intimately connected through the weather systems, and so there are the risk of increased drought. We can actually understand some of that from Antarctica. And then there's sort of the geopolitics. Sea level is very important to our Indo-Pacific island nations, a very important sphere of influence, but Antarctica has direct impacts on that with its contributions to sea level. So we claim 42% of Antarctica is part of the Australian Antarctic Territory. So these things are some of the things that are important about Antarctica. So I just want to talk about the connection between Australia and Antarctica and give you an illustration. So this figure, if you can see, has Australia here and Antarctica. And of course, mid-latitude storms, they originate in the Southern Ocean. There are the blocking events, there's cold weather outbreaks, there's heat waves. All of these sorts of events connect Antarctica to Australia. And you can see it in the next slide through ice cores. Ice cores, Antarctica is a fantastic place for ice core collection. And here is an example in the bottom right-hand side. You can see the formation of the bubbles, which give us a sense of the past composition of the atmosphere trapped in each of these bubbles once the bubbles close off from the snow that fell at the surface. And if you take those ice cores, you can have sub-seasonal resolution in them. You can actually look at the relationship between an ice core taken in Antarctica and the Australian continent. This is, in this case, precipitation. And what you can see is that for these particular ice core, it's highly correlated with the southern part of Queensland and northern part of New South Wales, east coast of Australia in general. And you can take the instrumental record, so that's like back to 1800, and you can understand that the rainfall, so this is a drought period here reflected in low sea salt over the Antarctic continent. This drought period here lines up with the instrumental record. But more importantly, you can take it right back into the past on millennial timescales. And the curious thing is that we discover that there are many droughts, and some of the droughts occur in long clusters like this one here from 1100 to 1200. So this is a century-long drought being recorded in the ice core. Information that we would not otherwise have from the simple records kept by manual methods by humans over the last 200 years. So it turns out, actually, we've been able to take these records, and the Queensland and the New South Wales water authorities have actually adjusted their dam risks and water supply based on the new statistics that they've got from the long-term drought periods that we had not understood because of the very limited perspective you get from instrumental records. Let me move on to, that's sort of showing the connection, but now let me move on to the next slide, he hopes. The next slide is really talking about the fact that we still have many problems in understanding the Southern Ocean, and this is a particular problem in the case of atmospheres. If you look at the Southern Ocean, if you go there in a ship, it's always cloudy. But if you actually look in the numerical simulations of the future climate, there are actually always clear skies. And so the challenge here, and it's very particular to the Southern Hemisphere, is why are those skies so clear? And it turns out, well, let me put it doesn't turn out, we think it's very much related to the different microbiota that live in the surface waters, generating aerosols, cloud nucleating particles, other vapours that creates the cloud droplets we need to form clouds. I happen to review many proposals for the Europeans, and there's a big interest in clouds in the Northern Hemisphere, but they do not have the same particular problems that we do for the Southern Ocean. And this problem has remained. And you can see this in the simulations. This is a comparison across, I don't know how many numerical models. And what you can see is that in every case, Antarctica is at the middle of each of these figures. In every case, almost every case, there is a excess of shortwave radiation landing over the surface of the Southern Ocean. And curiously, this excess of radiation is about 10 to 25 watts per metre square. And if you think about it, the story of climate change is about 1.9 watts per metre squared if you have a 1.5 degree target by 2100, 8.5 if you take a very high emissions pathway. So this bias is actually quite large relative to the scale of the climate change signal. And consequently, we are working collectively to understand the particular relationship. We don't have this bias in the Northern Hemisphere. To understand this particular relationship for the Southern Ocean. And that's program underway. And I'm now thinking about sea ice, and it's what I'll talk about is some of the work by Ed Doddridge and others. But we've had a remarkable events happen in the last 3 years, but there was a sort of a lead up to it. Here you can see, and there's no mouse, so we just, I daren't press this button actually, David.
No.
And let's stick a laser point in. What you can see here is the record of sea ice from the late 1970s through to, let's say, 2016. And when I was involved in the IPCC in 2007 and 2014, we were writing about how the sea ice extent was actually increasing at roughly 2% per decade. Remarkably, right, going in the wrong direction. Actually, we expect it to have been shrinking around Antarctica. And then in 2016, it sort of collapsed, but it actually over the next couple of years it recovered, and then it's collapsed again through to 2024. This shift is, and I'll show it in more detail here, is actually extraordinarily prominent. This figure here, which is now out of date, as of in the last week, the sea ice minimum here is actually tracked back down to near record low levels. So for the third year in running, and the winter of last year was actually the second lowest on record, with the record sea ice maximum extent in 2023. Our scientists were caught unawares. This was actually a surprisingly extraordinary event in terms of its probabilities. And what we've kind of come to realise is perhaps there is a real shift going on. And this is the work from Ed and Will Hobbs. And if you think about it, systems that are actually at a tipping point often have a dynamical change. If you're at a tipping point, you tend to oscillate more and more. If you're at a tipping point, you tend to actually have more lengthy serial correlations. You can think of it as a pendulum, if you like, and it's about to flip over. And at that point, actually, the variance goes up, and it's correlated longer over time. And this is sort of reflected, while not shown for the serial correlation. You can see the increased variance in the second half of the record from about 2006 onwards. Curiously, there is this period of high sea ice associated with cooler temperatures in the upper ocean. So the sea ice is, of course, sitting on the ocean. It interacts with the ocean and the atmosphere together. And then in this period of rapid decline, extraordinary decline, improbable gobsmacking, as some of my colleagues would say, there is actually a significant warming in the surface oceans. So this is sort of giving us a hint of actually the mechanisms behind the rapid changes that we've seen in sea ice, particularly in the last few years. So the alert, if you like, from this discussion is that we don't know enough about the atmosphere. The sea ice is shifting, but now let's talk about things that are going on in the ocean. And here I'm going to kind of give you a very rapid discussion of the overturning circulation. I'm going to simplify it as this is schematic, but it just illustrates the point. In the Southern Ocean, we have the strong westerly winds here. They actually push the surface currents northwards. The winds turn to easterlies near the Antarctic continent, and they push the surface waters southwards. The extraordinary katabatics that come off the continent, they cause sea ice formation, growth and production. But in creating that sea ice, you actually make the waters dense on the shelf, and those dense waters actually flow down the continental shelf into the abyss, and they become what we call Antarctic bottom waters. Antarctica is the source of the densest waters on this planet. There's the North Atlantic overturning circulation, but actually the Southern Ocean's the source of the densest waters in the world. They drive what we call the thermohaline circulation. And one of the challenges is that we'd like to understand what's going on with the overturning circulation. And this picture here, and this picture's right, of course, if you look at it, Antarctica is the centre of the planet in an ocean circulation sense. Some waters form in the North Atlantic. They return on this scale. They cross the equator. They head around the Antarctic continent. They spread out into the Indian and the Pacific Oceans. The question is, and there have been many articles, that this overturning circulation could collapse. And so the question for us, studying the Southern Ocean, is whether this circulation over the Southern Ocean is collapsing. And we have this little movie here, and this is actually from a set of simulations by the group, and I'm hoping that will work. And what this simulation is it's forced with a warming climate, and you can see here's Australia, the Australian Antarctic Basin, the deep basins of the Pacific and of the Pacific and I'm confusing my ocean basins. This is the North Atlantic. And what you can see in this little movie, and we'll play it again. Oops. What you can see is that the 4,000 metre layer in the ocean here is, maybe it will work, is progressively warming up. And then what we have on the right-hand side here is the overturning circulation. It's the strength of the deep overturning circulation in around Antarctica itself. And what it's showing is that by the end, by 2050, that there's a 42% decline in that overturning circulation. And so the question, and by the way, these are the observations that we understand for the Southern Ocean. There are very few observations of the deepest waters, but what we can see is that most of the deep warming in the global oceans is actually originating from the Southern Ocean, and there's very little change in the deep oceans in the Northern Hemisphere, completely consistent with the idea of this circulation overturning. I'd love to show the movie again, but never mind. So what we think is going on, and this is work from people here in Hobart, is that we have the ice shelves melting. They're freshening the surface waters around Antarctica. Because they're freshening, the water's becoming a little bit less dense, and so they can't flow down the slope of the continental shelves and fill the abyss in the same way. And so there's a reduction. And then as you reduce it, the warmer waters tend to move towards the Antarctic continent itself. And so we have been doing some work on that. One of my students, we've been working on sea surface height, Richard, looking at the sea surface height around Antarctica in these three particular basins. And we have a method for taking the sea surface height expression and actually projecting that to the deepest parts of the global oceans. And it works quite well in the case of Antarctica. And this is the trend here that we project from the basis of the sea surface height at 4,000 metres for the three basins that I showed you in the movie. And if you compare it with the direct observations taken from ships represented by these lines, you see there's quite a reasonable correspondence between the two. But this is a measurement. It's not a simulation. It's not through a model. This is actually pretty much an observation of those deep temperature changes. And you can calculate the volume change of those bottom waters with the bottom waters, the bottom half of the water column, And you can see that it's decreased by, turns out to be 1 spur drip, 10 to the 6 cubic metres per second of loss progressively since 1992 through 2020. And remarkably, and if you remember the 42% decline of the overturning circulation in the movie from the last slide, remarkably over this shorter period we can see that the volume of those bottom waters has actually declined by 15%, and if we went in the same linear way, not through any tipping, it would exceed 30% by the 2035, not very far away in time. But what this opens up is the prospect of actually being able to monitor that overturning circulation around Antarctica. And I think that is particularly unique. So it's useful. I've moved from the bottom water, I'm now moving out from Antarctica, but it's just very useful to remind ourselves how important the oceans are in the global system. This is a figure that came out of the 4th assessment report in 2007. This is a sort of a figure that summarises what's in this figure here. The incoming solar radiation is changing, and there's less going out because of the increased greenhouse gases around the planet Earth. 1% of that energy is retained in the atmosphere. So the atmosphere is peripheral to the discussion of energy balances in the planet. 91% of the energy is retained in the oceans. So the oceans are central to the storage of new energy in the Earth system. But 3% actually is what is involved in the melt of Antarctica, the melt of Greenland and multi-year ice, and the land itself, the terrestrial parts warming up, and that represents 5% of the total energy change. Now, remarkably, the Southern Ocean and the Southern Hemisphere is the fastest part of the Earth that's warming up. So this blue line here is the amount of energy retained in the Northern Hemisphere. The red line is the amount of energy that's retained in the Southern Hemisphere. And you can see that this slope is about twice the slope of the blue line. And why is that? So the very long-term change is very likely to be due to the fact that there's a lot of aerosols, a lot of sulfate particles in the Northern Hemisphere. So the Northern Hemisphere, they reflect light into space, and that leaves the Northern Hemisphere warming at a slower rate. The red is because actually the Southern Hemisphere is very clean, and the rate of heat uptake is actually higher. But curiously, in this particular period here, the rate of warming in the Northern Hemisphere went to 0, and all of the warming actually occurred in the Southern Hemisphere. And that's a little bit remarkable. So that's telling us that there's a kind of a major difference between the Northern and Southern Hemisphere over that decade between 2004 and 2016. And you can say, well, that's curious. There's a lot of heat being stored in this part of the ocean. I'm hoping you can see the pointer there. Actually, it's a red pointer in a red ocean, but it's in this part of the ocean. And if you think about it, there's a lot of energy being stored here. It turns out, if you look at this last picture, there's about 280 zetajoules. I know, it's a funny number, it's a lot. And just to give you a sense of what that amount of energy could do, if we were able to transport it from the northern side of the Antarctic circumpolar current, right? So it's just an experiment. We're going to move the heat to Antarctica itself. We would actually, and if all that heat went to melting it, we'd get 2.3 metres of sea level rise straight off. So that tells you something about how important the way the planet actually moves heat from north of the Antarctic circumpolar current to Antarctica itself. And the Antarctic circumpolar current is therefore actually a barrier to that heat going into Antarctica. So you don't never see the 2.3 directly. But if you project in climate change, it's going to continue to rise. And in fact, whatever we do, even if we stabilise the planet in the surface temperature, that heat will continue to accumulate in the global oceans. For a low emissions trajectory, it will be 2 to 4 times. For a high emissions trajectory, 4 to 7 times. So that heat is being stored in the ocean as a service to humanity. But let me kind of conceptualise this up a little bit. Every joule we store in the oceans, if we were to get it to Antarctica, we'd actually get a lot more sea level. And you can see that in these two inventory graphs here. On the left side, this is the one about energy, and on the right side, this is the one about the sea level budget. So most of the energy is stored in the oceans. That's the two blue colours here. But if you look over here, the ocean, through thermal expansion, is only contributing this much. And the 3%, which is down here, goes into the melting of the sea ice and of the ice sheet, and Antarctica is actually contributing this amount. It turns out that for every joule that you can get to Antarctica or to the Greenland, you can get 40 times more equivalent sea level from it than you can from a joule that just expands the water column in the oceans itself. And so this transport of heat to the continent, to the Greenland or to Antarctica, is a critical element of our thinking for future sea level. How am I doing on time, Richard?
Take your time.
So let's talk about sea level and the risks that Antarctica provides us with. In the long term, sea level is all about the future of the Antarctic continent. And there are two major risks around the Antarctic continent. There should be a movie there, but let's see whether it comes up. The first one is what we call marine ice sheet instability, or marine ice sheet cliff instability. And that's actually where there's a nice little, yeah, look at that. I just found the movie. And here's an example of it. This is the Larsen B ice shelf that cracked up in the space of 3 or 4 months. It caused an acceleration of the ice streams behind, and that was, in terms of climate, instantaneous. That led to something like 1/4 of a millimetre of additional sea level that year from that ice sheet alone. And that's an example of the marine ice cliff instability. It's caused really by the freezing of fresh water in the ice shelf itself, which leads to a fracturing of the ice shelf itself. And when you fracture the ice shelf, it thins this and it causes an acceleration of the ice sheet towards the oceans. So that's one kind of mechanism. And then there's a second one, which is what we call marine ice sheet instability, and it's around this retrograde slope. So this is the continental slope, continental shelf, continental slope goes off to the north here. Here is the ice sheet, here's the ice shelf. And if you have a little bit of warm water creep in here, that warm water accelerates the melt here. It actually moves back a little bit. That actually changes the thermodynamic temperature difference between freezing. It accelerates the melt a little bit further. And because it's retrograde, it continues to provide a positive feedback in that instance. The ice sheet responds by thinning and accelerating, and will continue to actually move backwards constantly until this slope becomes positive again. And so that is once you kick it off, it actually continues to lose and melt and provide mass to the global oceans. Now, in the 80s, we understood that the West Antarctic ice shelf, this area here, was at the risk of melting. But in the 80s, we didn't know about this area of East Antarctica, part of the East Antarctic territory that Australia claims. Here we have the, I hope I get this right, the Wilkes subglacial basin and the Aurora subglacial basin. And these two basins themselves are actually submerged below sea level, and both have retrograde slopes in them, and both are susceptible to marine ice sheet instability. And in here, there's actually 10 metres of potential sea level locked up. We won't get 10 metres, but there is that sort of volume. And it's these two kinds of risks that caused, in the last report of the IPCC, to draw this line on here. So this is a figure of what we estimate as the future sea level of 2300 for a high emission scenario. This is what we think the future sea level would be if we stabilised the planet by 2300. So sea level will still be in excess of 2 metres by 2300. And then we have these estimates here for the various scenarios by the end of the century. But they added in, I wasn't part of this report, they added in this line, and they talked about low confidence, high impact ice sheet instabilities, the things we didn't know when the Rumsfeldian view of the world, the unknown knowns, or whatever that expression goes. And so what they were highlighting was the risk associated with the collapse of the Antarctic ice sheet. Now that risk isn't immediate, and this is a set of simulations carried out at the AAPP and ACES at the University of Tasmania, and you can see these two basins, the Wilkes subglacial basin and the Aurora subglacial basin, and that this figure is really pointing to these two boxes. And you don't have to be able to read these two boxes, but the most important thing is to understand that the threshold for which they start to accelerate is in 2150. So the danger isn't immediate. The danger is actually well into the future. But we're increasingly, as we get new knowledge, becoming kind of confident that that is a real danger going into the future, even if we stabilise the climate. So let me kind of finish up. What I've done is I always love this discussion around impact, but what I've done is kind of highlighted a suite of risks that Antarctica and the Southern Ocean presents to us collectively. And those risks are around tipping points, the changing nature of sea ice, the risks around the Southern Ocean and the huge storage of heat there and how that might travel to Antarctica, and then the risk of ice sheet and ice sheet instabilities. So this is, I think, critical knowledge. It's the sort of thing that's gone into the IPCC and the various roles that has had over, contentious roles that that's had over the last 30 years. My organisation produces insight papers, so we report on those and talk to them. Or generally, our research is used by water authorities, the Conservation Convention of Antarctic Marine Living Resources. But let me just kind of finish up by saying we were caught out in 2023 when sea ice suddenly collapsed. We didn't understand the reasons. And I think that's because we don't have a mindset in the climate community of also tracking things rapidly, on time, in real time, and understanding and distributing the information. It takes a decade to actually understand that the climate system's changed usually, but we need to narrow that. We need to narrow it to just a couple of years at best. We should have peak carbon in before 2030. But how would you know that you'd succeeded and that your policy responses were right beyond 2030 unless you actually could track the current climate system, in this case track Antarctica, track the ice sheet accurately enough, fast enough to say that yes, that mitigation has made a difference. And I think there's a real urgency to be able to do that in advance of knowing where this planet's going. Thank you.
Thanks very much, Nathan, for a very interesting talk that's going to have consequences for everyone, let alone in Australia. But yeah, happy to open the floor to questions.
Microphone here.
While people are thinking about it, I'll have a few for you.
Thank you, Richard.
So timescales on these changes, how confident do you think people are in being able to do it from?
Can you just repeat?
So Richard's asked on what timescales of the changes.
Well, confident certainly from the ocean side. So I guess I'm alluding to what sort of observing systems do you need for your point of being able to track it in sort of pseudo real time to be able to predict.
So for ice sheets, it's different for every system. Yeah. So for ice sheets, maybe we actually have a sufficient observing system, but maybe we need more accurate projections. The timescales there have actually shocked us. If you look at the GRACE experiment, the GRACE is a gravitometry measurement of the mass of Antarctica or the mass of Greenland, and it's started in, I guess, about 2000, and what it shows is it's sort of flat and then it's gone with a bend in the curve like that, and it's accelerating. So that's actually got, over a 20-year record, we have an identifiable loss of mass over Antarctica and Greenland to the point where tracking more accurately, if you think about that, that's decade timescales. We never really imagined ice sheets having that short a time frame, actually. So there's information in a short time. We don't have a long record for ice sheets, except perhaps in some paleoclimate circumstances. For the oceans, I think we need to actually understand the oceans on a 2 or 3 or 4 year time scale, much shorter than we used to think. When I first arrived at the ACRC, the oceans were static, right? And now we don't think that at all. We've actually shifted dramatically from static to, oh yeah, it's varying and it's mostly climate change in the Southern Ocean, but in the other oceans, a slightly different set of timescales. For sea ice, right, that record, it changed in 2 years, basically, from a peak in 2014 to a trough in 2016. You're getting a sense.
Could you explain the implications of the A23A?
Sorry, say that again.
Could you explain the implications of the glacier A23A going north?
Yeah, so it's just grounded. Is that the one you're talking about? Yeah. It's not, so I can't tell you about that particular glacier, but if you think about all of the glaciers that break off, it's about 50% of the mass loss by Antarctica itself. That's actually freshening the surface waters, changing the stability of the oceans. If you accelerate that rate and along with increased melt, then you would lead to less of that bottom water I talked about, and you also would change the balance for sea ice formation on a year-to-year basis. Ed is a better person to ask on that question, but I venture actually the freshening would lead to a reduction of the speed of the Antarctic circumpole current, changes in the rate of water masses on the northern side of it, and a collapse of a slowing of the overturn.
Thank you. Yeah, Andy, it's just coming down.
Thank you, Nathan. I have a question regarding emissions pathways. So it's become I guess maybe more prevalent the idea of overshoot pathways when it comes to emissions and warming thresholds. However, the issue with that you might be aware of is that there's unclear regional responses. Do you have any idea how Antarctica might respond differently to, for instance, the Northern Hemisphere if an overshoot pathway was, I guess, undertaken?
I feel the questioner knows more than me. So my response to that would be, it presumes something, doesn't it? It presumes that we are actually in control of CO2 in the atmosphere, and then we can draw it down and thereby take it out. And therefore it presumes that we have all the technologies to do that job. And so then I'm just a little bit sceptical, because you've yet to have a real demonstration of the capacity to draw down CO2 in a human-directed way. There's a very limited capacity in the volume of terrestrial carbon that can be stored in trees. That's 200 gigatons. That will run out at a certain point. So I'm kind of sceptical that we can actually embark on deliberate overshoots and have the view that we can manipulate the atmosphere enough to fix it up. We're having trouble with the zero thought of policy, which is simply to stop emitting. Right. So, but there is hysteresis in the system. The Antarctic ice sheet is an interesting one, because once you kick it off, it continues to lose mass even if you fixed up the temperatures out the front. Okay, so it's a one-way trip on the time scale, long time scale, relative to, so some things we can't actually recover, and that's one of them.
I'm just wondering, we knew that once upon a time there was Gondwana with the trees and things on Antarctica, so the ice has come. Do you think now that maybe the Earth's axis is changing and this is all just going back to how it used to be? Oh, it's might be a silly question, but it's just something that's...
The question of, so the Australian Antarctic Division and my organisation are involved in the Million-Year Ice Core. And the Million-Year Ice Core is where we take a traverse and they drill. And we're going to drill to 1.2, 1.3 million years ago. And so all of the climate change in the past is likely to be just orbital variations. And there's something very nice when you get beyond 400,000 years, you get, or 800, I'm not quite sure of the number, the frequency of ice ages actually widens very significantly, and so you can actually look at a different set of orbital parameters. And so that's sort of your question. And we're hoping to get the answers in the next few years. So maybe you can invite one of my colleagues back and have a discussion about that.
Yeah, 8 years away.
8. Is it 8?
Well, by the time they get them, and then we'll...
Last question?
Yeah. Any more questions at all? Just down the back.
So, Nathan, it's not often we have such easy access to an expert on Antarctica and climate change, and a person who could probably give us an idea about what the impact is going to be of moves in the US at the moment. So the US president leading the country to go back to excessive use of fossil fuels and withdrawal from the protocol. I can't repeat the correct name of it, but that international agreement about trying to mitigate climate change, and there's probably other aspects that I just don't have the knowledge of. So I'd be really keen to hear what you think, what direction this is going to take the world.
Well, I think we're on Yeah, we should just wait, actually. Mr. Trump's full of bluster and negotiating positions, and there may yet be a different story. So, fingers crossed. We're still on a high trajectory, actually. We're not anywhere meeting the 1.5 temperature ambition, so it's a 1.9 watts per metre squared by the end of the century. We're more on a 3 degree. And so if it came to Trump and America totally leaving and the drill baby drill scenario actually follows, then I think, America's the second biggest emitter in the world, so that just means that we'll ratchet up from 3 to 3.5 or 3.7 degrees. But the real problem is that it erodes the whole of the Paris Agreement, and that might come undone, and that would be a shame. That would be a definite shame, because any progress is beneficial, actually. Any progress, even if we don't meet the 1.5. So we've got to keep that ambition up. I feel like we're entering the dark ages in America, I'm afraid, and that is the challenge, actually. It seems like the scientists at NOAA have done too good a job. They've now become a target because it's too easy to target them as distinct from actually following the science. That's a sign of the dark age, isn't it?
Yes. All right. Can everyone please join me in thanking Nathan for